Hey everyone, welcome to this explainer. Let's jump right into it. Today, we're exploring a brilliant, honestly beautiful idea that fundamentally shifted our entire understanding of physics. We're unpacking the Bohr model of the atom. We're going to look at how Niels Bohr took this chaotic, unpredictable, microscopic world and applied a set of elegant, strict rules to it. It's a fascinating look at how human ingenuity allowed us to see the building blocks of the universe in a completely new light. Okay, let's dive into this. When you picture an atom in your head, what do you see? We usually default to that classic, iconic image, right? A tight cluster of particles in the middle, surrounded by these rings with electrons whizzing around at crazy angles. But for a really long time, physicists completely struggled to figure out a mathematical model that actually supported that visual. That search for structure is exactly what led to the concept we're exploring today. To really grasp Bohr's breakthrough, we kind of have to look at the analogy physicists were working with at the time. The atom as a miniature solar system. And, it makes intuitive sense. You have a heavy, dense nucleus sitting at the center, acting like the sun, and you have these tiny electrons revolving around it like planets. But there is a massive, fundamental difference between the two. In our actual solar system, a planet could theoretically orbit the sun at any arbitrary distance, as long as it has the precise speed. But electrons, they don't play by planetary rules. Instead, they are strictly confined to fixed allowed energy shells. They aren't free-roaming at all. They're completely locked into specific, invisible tracks. Section 1. Bohr's 3 fixed rules. Let's see how Niels Bohr fundamentally established the laws of physics for this tiny quantum universe. Here's rule number 1. Fixed orbits. Electrons move only in specific, stable, circular orbits around the nucleus, and they do it without losing any energy. Now, why is that last part, the not losing energy bit, absolutely crucial? Well, according to the classical physics of the time, an electron moving in a circle should constantly give off radiation. It should bleed energy, spiral inward, and crash right into the nucleus in a fraction of a second. If classical physics were right, all matter in the universe would just instantly collapse. Bohr bravely proposed a radical workaround. He said that these specific orbits are essentially magic safe zones. As long as an electron stays in its specific lane, it is perfectly stable. It loses absolutely zero energy. So what actually dictates these safe zones? That brings us to rule number 2, quantized energy. Every specific orbit has a fixed energy value. What quantized means here is just that the energy comes in strict, discrete packets. The electrons can't just have any arbitrary amount of energy. Think of it like standing on a staircase rather than walking up a ramp. On a ramp, you can stop at literally any exact elevation you want. But on a staircase, you can stand on the first step or you can stand on the second step. You cannot hover in midair between step 1 and step 2. The electrons are forced to be on a specific step. They are locked into these strict, non-negotiable energy levels. Which naturally leads us to the third rule, energy transitions. If an electron is stuck on a specific stair step, can it ever move? Yes, but only by absorbing or emitting energy. Because they can't exist between the steps, an electron moving from one energy level to another doesn't actually travel through the space in between. It basically disappears from one orbit and instantaneously reappears in another. It's a dynamic, sudden process, and it's the actual mechanism for movement within the atom. Section 2. Making the quantum leap. Highlighting this jumping mechanism is absolutely key because it's the core of what makes Bohr's model so revolutionary. Let's actually walk through the mechanics of a quantum leap. Think of it as a two-way street. Step 1. If an electron wants to climb up the atomic ladder and move to a higher, larger orbit further away from the nucleus, it has to absorb an exact, precise amount of energy to make the jump. Step 2. If that electron wants to drop back down to a lower orbit, closer to the nucleus, it must get rid of that exact same amount of energy, and it does that by emitting it out into the universe. Absorb energy to climb up, emit energy to drop down. It is an incredibly precise exchange. Now, what's really interesting about this slide is the math behind that exact energy exchange. And don't let the equation intimidate you, it's actually incredibly elegant. Delta E equals HF. This formula mathematically defines the exact energy of the light that gets emitted when an electron drops to a lower step. Let's decode what these variables actually mean. This breaks it down beautifully, instantly showing us the connection between the invisible atom and the visible world we live in. Delta E is simply the energy difference between the two levels the electron is jumping between. The H is Planck's constant, a fundamental number in physics that just makes the math work out perfectly. But F F is the magic variable here. F stands for the frequency of the emitted or absorbed light. This means the exact amount of energy the electron gives off perfectly dictates the frequency or the color of the light we can actually measure. When you look at a glowing neon sign or those magnificent colors of a nebula in deep space, you are literally looking at trillions of electrons executing exact quantum leaps and emitting very specific frequencies of light based on this exact equation. How cool is that? Section 3, Triumphs and Limitations. Now let's pivot and objectively evaluate how well this elegant model actually worked in scientific practice. So the model had some massive world-changing achievements, for sure, but it also had some glaring issues. On the plus side, it successfully explained atomic stability, finally answering why atoms don't just collapse on themselves. It perfectly explained the hydrogen line spectra, predicting the exact colors of light that hydrogen emits. And it really heavily supported the entire burgeoning field of quantum theory. But look at the limitations on the other side. Bohr's math worked miraculously well for hydrogen, which has exactly one electron. But if you added just one single extra electron to the mix, like say in a helium atom, the math basically fell apart. No way, right? It couldn't explain multi-electron atoms at all. And as our telescopes and microscopes got better, we realized it couldn't explain the really fine microscopic details of the light spectra either. It was a brilliant theory, but it was strictly limited to hydrogen and atoms behaving exactly like hydrogen. Section 4. Why Bohr's model matters. Let's look at the legacy of this model and bring it back to the big picture of why we care about an imperfect theory. Seriously, if it fundamentally failed for almost every element on the periodic table except hydrogen, why do we still care? Why is it still taught in every physics classroom in the world? Well, we care because despite its major flaws with complex atoms, it was the ultimate pioneer. It was the very first successful quantum model of the atom. Before Bohr, the quantum world was kind of just theoretical guesswork. Bohr gave it structure. He introduced the undeniable reality of quantized energy levels, proving that the universe operates in discrete steps rather than a smooth, continuous flow. Because of that breakthrough, it became the absolute foundation for modern atomic physics. Every single complex, highly accurate quantum model we have today was built directly upon the foundation that Niels Bohr poured. If you want to commit the absolute essence of this explainer to memory, this is the definitive summary. Bohr proposed that electrons occupy fixed energy levels and emit or absorb energy when jumping between them. That single sentence right there represents a monumental leap in human intelligence. It acts as the fundamental scientific law for the glowing lights in our cities, the lasers in our technology, and the starlight in our sky. But as you've seen today, the story doesn't end with Bohr. His model was a stepping stone. It was perfectly accurate for one electron, but utterly lost when faced with the full, messy complexity of the universe. Which leaves us with a truly fascinating question to ponder. If Bohr's structured planetary model couldn't explain the atoms making up your body, the Earth, and the complex chemistry of the cosmos, what does the real atom actually look like? What bizarre, mind-bending quantum reality replaced these neat and tidy circular orbits? Well, you'll just have to keep that curiosity alive until our next explainer. Thank you so much for learning with me today. Keep asking great questions, and I'll catch you next time.